said, I'm going to talk about how we are actually running pipelines in our user interface. And so I will show you our publicly available pipelines, and I'm going to show you how we are actually running the pipelines in short videos. So this is our web server called, you can access with DolphinNext.umassmed.edu, and this is our homepage where all the publicly available pipelines are listed. And if you click one of these pipelines, you're gonna see the content of it. So all the workflow, all the steps that pipeline execute is visualized in this workflow. So if you just click the run button at the top right, it will send you to the run page, and you need to just enter some input parameters to start your run. And before going into details, I will show you how many publicly available pipelines we have. So basically, one of the most used pipeline is RNA-seq pipeline. And inside this pipeline, we have multiple options for the genomic alignment. So it allows you to align with the HiStat2, star, or TopHat2. And the star is enabled by default. And if you want to compare the other aligner results in the same pipeline, you can enable them as well. So you will get a consolidated table in the report section. For the gene expression levels, you can use RSAM or feature counts. So in our last session, we used RSAM to get expression count tables. So you can do the same thing with DolphinNext. And after the RSAM analysis, you can do this differential expression analysis in our report section by using DE browser. So we integrated DE browser inside in our report tab, and you can use the different methods to do your differential expression analysis. You can use DE-seq2, HR, or Lima inside this interactive tool. So next, we have this ATAC-seq and the ChIP-seq pipelines. Inside these pipelines, we do the genomic alignment with both I2. And for the peak calling, we are using MAX2. And again, we have a similar differential analysis embedded in our report section. So you can do your analysis with the DE browser. So please keep in mind that we have a lot of sub-modules inside of these pipelines. We have an adapter removal, trimmer, quality filtering, and sequential mapping embedded in these pipelines. And we are reusing these modules again and again inside the different pipelines. And for the quality control purposes, for the raw reads, we use FastQC to see any kind of a problem inside our raw reads. And after alignment, we get our BEM files, and we can do some quality checks on those BEM files using RCQC and the Picard. And for the visualization purposes, we can create IGV or the UCSCG genome browser compatible files. They called TDF and BigQuick files. We can create those files inside the pipeline. So next, we have a bunch of single cell pipelines available. One of the most used one is Cell Ranger, which is created by the 10x company. We have embedded this Cell Ranger software into our system. So basically, if you choose Cell Ranger pipeline or the Cell Ranger ATAC pipeline, you will use 10x Genomics software. And after you do the analysis, you can load your output files to this Loop cell browser to visualize your data in this software. And Alternatively, we created two different pipelines in our Garber lab. They call 10x Genomics pipeline and the Invro pipeline. And we do our alignment manually, so we can choose different type of aligners. And in the Cell Ranger, it's like a package that you cannot easily change your aligner or the counting methods, but you can do a lot of adjustments in these pipelines. So we use mostly star for the alignment, and then for the quantification purposes, we are using ESAT. And after doing all the analysis, we got this kind of a visualization by these R packages. So you can load your output files into SURAT package, R package, or signaling single cell packages to visualize your data. And if you are interested in the pRNAs, you can use these PyPipes pipelines. And these pipelines created by the Zimmer Lab members. And again, we embedded this software in our tool, so people can execute the same software inside our system. And so this is going to be a short video and how we are really executing a pipeline. So I will click this one of the RNA-seq pipeline in our homepage. And this is how our workflow looks like. And I will click this run button at the top right. And it will open up on this window where I need to enter a new project. I'm gonna call it test, then choose that project and click the select button. Now it's asking me to enter a run name. I enter test run. Now it will send me to the run page. So over here, first thing that I need to do is enter my work directory. I entered my home directory over here. If you are you are planning to use your home directory, you have 50 gigabytes of space available. And if you are using a really big files, then you need to consider using a project space or the NL space. And so next thing is you're going to choose your run environment. So I created these run environment for your account. If you don't see your environment listed over here in a drop down, please send an email into biocore.umassmed.edu. I will add those run environments into your system. And then next we need to choose our files that's going to be analyzed. So right now I directly choose the files that are already added into our window like this. But in your case, you need to click this add file button at the top right to add your reads. And I will talk about this functionality in the next slide. So next thing that we need to do is I need to specify whether these reads are in a paired format or a single format. I'm going to choose with this made field. And next, I'm going to choose the genome build parameter. I choose mouse, for example. Now I change this run. I enabled top hat by changing this option to yes. And if I click the settings icon just next to it, I can change the parameters that top hat gonna use. They all have these kind of a settings buttons just next to them, so you can adjust their parameters accordingly. And as by default, RSM and star is enabled by the default, so I didn't change anything on those. And I enabled IRC-QC this will create a read distribution after the genomic alignment. And then I'm gonna enable the trimmer, and I'm gonna remove few nucleotides from 5 prime, for example, one nucleotide, and from the 3 prime, I'm gonna remove one nucleotide as an example. And I'm gonna enable FastQC, and I will enable run sequential mapping. Over here, I can enter set of sequence, so it will align to those RNA sequences first before doing the main genomic alignment. And so first I will remove RNAs, then tRNAs, and finally I will just align to repeat masker, but it will not filter out those sequences. And now your pipeline is ready to run. So this button will turn into green. And before starting to run, let me talk about this adding files. So next slide, I will talk about those. One option is adding NCBI geo files into this run. So you can come to this field, click Add File button. Now we have a bunch of tabs available. You're gonna choose this Geo NCBI Files tab. Over here, you can enter different geo IDs into this field and click Search button. So as you can see, all the FASTQ files that are defined inside this GeoID is listed over here. So what you need to do is just choose the ones that you would like to use in the pipeline. So I choose the 3 of them and it added into this table. I can rename those files over here. And the next thing that I need to do is enter some collection name. I call it Vernier dataset and save it. Now those 3 files are selected into this pipeline. Next example gonna be adding a paired files. I'm gonna again click this enter file button. Again, I will click add file. Now I'm gonna search the path of the file that are located. So when I click the search button, it will show me all the existing files inside of this directory. And now I'm gonna choose the file type. It's already FASTQ, so I'm not going to change this. And for the collection type, it's going to be the paired list. And since I choose the paired list, I need to enter 2 patterns. So one of them is forward pattern and the other one is reverse pattern to match the paired reads. So for the forward pattern is .r1 and for the reverse it's .r2. If your files end up with underscore R1 or underscore R2, you need to enter these patterns to match these files like this. Then you have few options, like you can choose multiple files at the same time with pressing Shift button, and then click this Add Selected Files button. If you do that one, they will add into this down table as a single sample. So all the R1 reads gonna be merged into a single file, and all the R2 reads gonna merge into a single file, and you will have only one pair of sample. And if you don't want to merge these files into a single file, you can just choose one of them and click Add Selected Files, or you can do all of them by clicking Add All Files button. So next, you're gonna enter this collection name and save. That's how you can enter your paired reads. So let's start our run and show you how it looks while executing. So a few tabs gonna appear after you click the run button. If you click the log tab, you can see this that your jobs submitted into this log file. You can see that at the beginning there are some directory paths where it shows you the sub work directory that this job is submitted. So if you go and check the content of this directory, you will see that what kind of a command is executed, what kind of input files were available in that folder, and what output files created after the job is completed. You can check those things inside the cluster. And when everything is done, you will have the status going to be show completed, and you will have few tabs for the execution reports. Inside this timeline report, you can check how much memory is used, how long it takes to execute a single process, and how long it waited in the queue to execute that single job. So the gray part means that it is waited in the queue. And that's how it looks like. And for the other CPU and the memory usages, we have created these reports as well. So you can compare and maybe you need to increase or decrease the entered requirements for the specific processes. So for example, maybe star is using really high amount of memory, and you might need to increase that amount, or maybe you enter the really high memory requirement in your pipeline, but the task doesn't use that much. So you might decrease those values while you are running the pipeline. You can use this advanced tab to play with those parameters. Next, let's check our run reports. At the top, we have this run notes section where you can enter your run-related comments and notes inside of this markdown format. So you can enter code blocks in it, or you can enter images, and you can do a lot of different things like this to show your run related nodes. If you want to attach some file, that's also possible. You can add some protocol, for example, inside the section and save it. So when the users come to see this run page, they can see how you executed the run and which protocol did you use inside this report tab. Next, we have this multi-QC report. And so this is a very nice interactive HTML file that summarizes all the steps that pipeline executed. Right now, I have this RSAM, RCQC, star, and the FastQC reports all consolidated in a single file. I can check how reads are aligned. So mapping rates I can check over here for RSAM. I can check the multi-mapping rates for each sample. And for the RCQC, I can see the read distributions over here. So like introns, UTRs, and all the percentages are listed over here. I can, again, similarly for the star alignment, I can see their results. And for the FastQC, we have a bunch of different reports. And the nicest thing is, as you can see, all the files are inside in a single graph. And when there's an outlier, this tool is going to show you that this file has some problem, like maybe you might need to remove the adapter sequence, or maybe maybe the quality of the initial part of the read is problematic, so you might trim those reads. You can do these kind of operations afterwards, after checking these quality reports. Next, we have this table called alignment summary. Over here, for each sample, you can see how much reads are available at first, and after we do this sequential mapping, how much reads removed from these samples. So RNAs, tRNAs, and repeat masker are shown in here, and afterwards it showed the RSAM star and the top hat results in a single table, so we can easily compare the alignment rates inside this table. Next, we have this RSAM output. So last week we consolidated these tables like this, and now we got our table for each sample in a single file. So if we wanted to download it, we can download easily. Or if we want to do the differential expression analysis, we can go to, again, this RSAM summary table and open it with a DE browser. So this will open up a DE browser interactive tool inside our web page. So you can do your filtration over here. So you can filter out, first of all, low counted genes, and then you can go to your differential expression analysis, select your genes that, so select your samples, and create these interactive plots. So you can zoom in, you can choose some certain region to create a heat map. So all these tools are in a kind of an interactive tool, so you can hover them. So each block could be visualized by changing the view type. So Apple will discuss a little bit more when it comes to the browser. So there are a lot of things are available with the browser. So next, I'm gonna show you this R Markdown report. So again, by using the same RSAM output, we are creating this R Markdown file. And if you wanna, and it creates a similar plots that actually the browser has, but it creates in a PDF format. And all the codes that it's used is shown in the left side. So the nice thing is when you want to change one of the parameters inside this left side, you can do that. So as an example, I'm going to change this fault change value. There's a threshold for the log2 fault change value. So I will make it 4 and click this run script. So this will execute this code and update the image accordingly. That's how this R Markdown section works. And finally, in my last slide, I would like to mention that our paper is published in BMC Genomics in 2020, and our repository could be found in GitHub. If you want to check our code, you can please go and check this, our code over here. And so if you use our system in your project, please cite this software. And now I think you can go to the session 1 MD first and do your first run. So you're gonna enter the DolphinNext web page. Again, if you have some kind of a login issues, please send us an email. I will reply as soon as possible. And you will create a project, create a run. Now enter enter the input parameters like this. And please make sure you enter your cluster username over here. So you need to change this username in your run. And of course, if you're gonna use your project directory, that's also possible. This is just an example. And so that's gonna be it. So we will give you 30 minutes for this step, and you will do the homework later. So we will be on Slack right now.